I'm from Beihang University. I'm here today to introduce my job in self-oscillating broadband optical frequency comm generation. We use an EML-based optoelectronic oscillator and a recirculating frequency shifter to do this job. This talk will be in 4 parts. In the first part, I'll introduce several applications of the optical frequency comm, the electro-optic frequency comms, and the self-oscillating OFC generator. In the second part, I'll talk about our experiment principles. Then in the third part, I'll show and discuss our experiment results. And finally, the conclusions of our job will be discussed. Now, let's move to the first part of my talk. The optical frequency comm, or the OFC, is originally developed to enhance the precision of atomic clocks. It has high mode frequency relations and high phase coherence. OFCs have been used in various applications, ranging from metrology to spectrograph calibration for exoplanet detections to fundamental physics. In more detail, it can be applied to spectroscopy measurement, optical imaging, distance measurements, calibration of spectrographs, arbitrary waveform generation, and RF photonics and telecommunications. There are multiple ways to generate OFCs, including mode-lock lasers, optical microresonators, electro-optic modulators, or the UMs, and nonlinear effects-based methods. Nowadays, the electro-optic frequency comm is favored by researchers because of its advantages as follows. It has high repetition frequency tunability, usually larger than 10 GHz, high flexibility, high spectral flattening, and so on. This picture is a Euro structure of an electro-optic frequency comms generator. It uses an intensity modulator and several phase modulators. It can generate OFCs with high flatness, but it needs an external RF source as a modulation signal source, which quality is difficult to guarantee. And it cannot produce many numbers of comms. To compensate for these deficiencies, the self-oscillating OFC generator using an optoelectronic oscillator, also called the OEO, is gradually coming into the view. Its structure is shown in this picture. It often has a laser, optical storage, and other OE converters and filters. The self-oscillating OFC generator has high phase noise performance, and no external RF source is required. Based on the above reasons, we propose a new type of self-oscillating OFC generator, which uses an EML-based OEO and a DP-MZM-based recirculating frequency shifter. The schematic diagram of self-oscillating broadband optical frequency comm generation is shown in this figure. In this picture, we show that the detailed working process of the device. There are 2 parts to this device. The optoelectronic oscillator, or the OEO, includes an electro-absorption modulated laser, also called the EML, and the recirculating frequency shifter, or the RFS, including a dual parallel Mach-Zehnder modulator. In step A, the EML OEO is launched and stabilized, so the continuous light wave from the EML is modulated and generates multiple sidebands. Then, in step B, one of the sidebands of the signal is reflected by the fiber Bragg grating. This is to ensure the best possible recirculating frequency shift effect. Then the rest of the signal from the FBG is transmitted through the FBG to remain oscillation in step C. Finally, in step D, the reflected signal in step B is then injected into the recirculating frequency shifter. The electrical signal from the EML OEO is also injected into the recirculating frequency shifter with a phase difference of 90 degrees. The recirculating frequency shifter shifts the sideband of the optical signal in each loop in one direction, so that it can generate the OFC with high frequency power flatness. In the OEO loop, we use an electro-absorption modulated laser, or the EML, as a laser and the EO modulator. It has several advantages, such as easy integration, low driving voltage, high modulation rate, compact structure, and so on. We also use a dual loop structure to improve the phase noise performance of the OEO. In the RFS, or recirculating frequency shifter loop, The electrical and optical signal is from the same source, which is the EML-OEO. The DP-MZM is settled to realize CSSB modulation to generate the OFCs. The direction of RFS is determined by the reserve sideband of CSSB modulation in DP-MZM. And the oscillation signal from the OEO is also defines the frequency interval of the RFS. The optical bandpass filter, also called the OBPF, is used to reshape and confine the optical spectrum, which can help to generate the broadband OFCs. This structure has been shown to generate optical frequency comps with more comps. Let's move to the experiment results of our job. These are some of the devices used in our experiments I listed here. A proving experiment on the setup is also shown. The output spectrum of the OEO of the EML-OEO, and that of the reflected signal by FPG are given in this picture. It's easy to say that the EML-OEO gets a stable oscillation, and the single positive first-order sideband is reflected by the FPG. The central wavelength of EML is about 1552 nanometers, and the reflected wavelength of FPG is about 5052.1 nanometers. So that you can see this sideband in figure A has been reflected and attenuated. Next, in this picture, we can see OEO's oscillation frequency is about 10 GHz, and the side-mode suppression ratio of the oscillation signal is also measured. For the 2 MHz side mode, the SMSR is about 44 dB, and for the 200 kHz side mode, the SMSR is about 62 dB. This phenomena is because the 100-meter short loop causes the side mode in 2 MHz, while the side mode in 200 kHz is caused by the 1 km long loops. This causes the side mode of the long loop to be enhanced and thus reduce the SMSR. The phase noise is also measured by electrical analyzer in this picture, and it is about minus 105.58 dBc per hertz at 10 kHz. The timing jitter of this 10 GHz oscillation signal can also be calculated to be 0.32 picoseconds from the phase noise result. We can also show that the optical spectrum of the CSSB modulated signal and the generated OFC. In this case, the RFS CSSB modulation is achieved, and the side-mode suppression ratio is 11 dB. 64-tone OFC with a line spacing of 10 GHz with a power variation of 7.7 dB is generated, and a 38-tone OFC with a flatness of 1.2 dB is in this case. And you may notice that the SNR of the OFC, also called the signal-to-noise ratio, is a bit poor, which is because we use the EDF's noise performance we use is not very good. So, in conclusion, a self-oscillating broadband OFC generator using an EML-based OEO and a DP-MZM-based RFS is proposed and experimentally demonstrated. A 10 GHz oscillation signal is generated employing the EML-based OEO, and the phase noise is minus 105.58 dBc per hertz and 10 kHz. And 64-tone FC with a line spacing of 10 GHz is produced with a power variation of 7.7 dB, and there are 38 tones with a flatness of 1.2 dB. So I have covered all the points that I needed to present today, and I'd like to thank you for taking time out to listen to my presentation. And if you have any questions, I'll do my best to answer them in the time we have remaining. Thank you.
Let's thank the speaker for this, I believe, pre-recorded talk. And I think the speaker is also online. I'm not sure if he is able to answer questions if there's any.